at tangent lines today. So I have our steps written up here, but I'm going to walk you through. So to write the equation of a tangent line, we need to have a slope and a point. So point slope form is y minus y1 equals m times x minus x1. And we need to have this memorized. We need to know how to write an equation of a line just from memory. So the two things we need are the m, that's our slope, and our point, an x and a y value to put there. So this first example has a fourth degree polynomial, and they want to know what is the tangent line at the point 1, 0. So we have x1 and we have y1. We need the slope. Well, slope is our derivative. So first step, find the derivative. So dy dx equals derivative of each of these individual ones. X to the fourth would turn into 4x to the third minus, we have 3x squared, bring that the 2 in front with the 3, so 3 times 2 is 6, x to the power of 1, and then the derivative of a constant is just 0, so I don't have to write that down. So this is the equation for slope of this tangent line, but I want it at a specific point. So we need to take this point, the x value, and sub it in. So our slope that we're about to use is at this specific point, so this 1 is going to be substituted here and here. So third power for 1, that's still just 1. So 4 times 1 is 4. Minus 6 times 1, which is 6. So my slope at that point is negative 2. Now that I have the slope and I have the point, I can simply just write the equation. Y minus y1, that's 0, equals m, that's what we just found, the slope, negative 2, and then x minus x1, that's 1. And you don't have to do any simplifying unless they say, okay, now put it in slope-intercept form. Then you would have to change some things around. But this one just says find the equation of the tangent line. So this is a perfectly good form for me. Next up, let's do it one more time. We have this equation that's a cubic, and we want the tangent line at the point negative 1, negative 2. So take your derivative. We have our x1, our y1. We need the slope, and slope is derivative. So 3 would come out front. X squared is what I have on that first one. The derivative of x is simply just 1. Now I have my equation for that slope. I need to take into consideration the point that I want it to pass through. So it's negative 1 for the x that I want. So the slope would be 3 times negative 1 to the power of 2 plus 1. Negative 1 to the power of 2, that's positive 1. 3 times 1 is 3. So 3 plus 1 is what I'm left with, which is 4. So now I have my slope and I have a point, so we just fill in y minus y1. Well, it's minus a negative, so let's make that plus 2. Equals m, that's my 4 that I just found, x minus x1. Well, that's a negative 1, so let's make it a plus 1. And that's how you find the equation of a tangent line at a specific point. Finding horizontal tangent lines is up next. So a couple of steps that we need to look at to find where a function has a horizontal tangent line. Take the derivative of the function and set the derivative equal to 0. A horizontal line looks like this right here, and it always has a slope equal to 0. So derivative is slope, so set the derivative equal to 0, and we can find where we want the horizontal tangents to occur. Let's look at this first example. So take the derivative, dy dx equals, if I do 3 times a third, that's 1, bring that power down, and we have x squared. Derivative of 4x is just 4, so we have minus 4. So this is my slope. I want to know where the horizontal tangents are going to occur. So I take the slope equal to 0. So you have a couple of options. You can factor this as a difference of squares, or you can just move the 4 over and get x squared equals 4. Take the square root of both sides, and what you need to remember if you do that is that it is both the positive and the negative 2. So you have 2 places where there's a horizontal tangent, at positive 2 and negative 2. Next up we have sine x plus 5. So take the derivative, dy dx, equals, derivative of sine is cosine. The derivative of 5, that's a constant, it's 0, it's gone. So now we think, okay, where is cosine x equal to 0? Think about your unit circle. Where is the x value 0? Well, that's up there at the top and at the bottom. So first x value is the half pi, and then 3 pi over 2. And then you can just keep going with that pattern over and over and over again, and you'll still get 0 as you go around the unit circle from there. One more on this one. Take the derivative. Derivative of 6x is 6. Derivative of negative 4 is 0. So if I take my slope 6 equal to 0, I don't have anything to solve. 6 is never going to equal 0, so there are no horizontal tangents. Which should make sense because this is a line. If I draw a line, there are no horizontal tangents that I could do to that. Let's look at just a little bit more. Right here, differentiability and continuity. There is an alternate definition of a derivative using limits that is useful. We've seen this one right here. Okay, so this is not a new thing right here, but we're going to look at a couple of different instances with this. We know that the derivative from, or the limit from the left has to equal the limit from the right. So there are a couple of instances that the derivative fails to exist, and an absolute value graph is one of those things. So the function that I'm going to consider is the absolute value of x minus 2. So this is simply just a absolute value graph shifted to the right 2. So instead of starting at 0, it's going to start right here, and it is actually drawn on here for you. It's just super light right here. So since we know that the derivative is slope, well, if I do the derivative from the left, the slope of this line right here, that has a slope of negative 1. So if I evaluated this limit, it would end up being negative 1. If I look at the derivative from the right, this is a positive slope, and that's a positive 1 slope. So if I evaluated this limit, it would have a value of 1. And you can see that the limit from the left does not equal the limit from the right. So we can say that since the one-sided limits are not equal, that limit doesn't exist. So we can conclude that that derivative is not differentiable and has no tangent line possible at x equals 2. So just at this one point, x equals 2, it's not differentiable. So there's no tangent line that can happen there. It is continuous everywhere, but that one point, and we call this point right here a cusp or a sharp turn, that's not going to be differentiable ever. Next up is a vertical tangent line. Whenever we get a vertical tangent line, we're also going to have a derivative that fails to exist. And let me show you here. So let the function be x to the power of 1/3, which we know is the cube root graph that we have over here that's happening. And I'm just going to trace it so it's darker. It's continuous at x equals 0. Show, like you can see, but the limit is actually going to fail. So if we take this limit definition and I substitute my f of x, I've got x to the power of 1/3 minus f of 0, 0 to the power of 1/3 is just 0, over x minus 0. I want to take the limit as it approaches 0. I want to do a little bit of simplifying first. So x to the third over x. We know that we can subtract these and we get 2/3, but that is left on the bottom right here, leaving me with a 1 in the numerator. So now I can actually do the substitution for that limit as x approaches 0. Well, 1 over 0 to the power of 2/3 is 0, and still, even after simplifying, it's giving me undefined. This vertical tangent that would actually happen right there is happening, and that's what we've got on the 1 over 0 being undefined. Okay, so last step. This does not mean that if a function is continuous, it is also differentiable. So I just showed you two places where they're not differentiable because of the undefined or the cusp. Graphs with either a vertical tangent or a sharp turn, we call that a cusp, are not differentiable at the point where those things occur. So that undefined slope that we found using that limit, or the sharp turn where the limits do not match on the left or right, is what this is talking about. So the derivative will fail to exist there.